Hey everyone, and welcome. Today we're diving into a big one of the most famous, most powerful reactions in all of organic chemistry. Yep, we're talking about the Sandmeyer reaction. Let's just jump right in. So let me ask you something. Imagine you're a chemist, right? You're staring at this super stable, really sturdy benzene ring. And your job? You've got to perform what's basically molecular surgery. You need to snip off one functional group and swap it for something else. Precisely. But how in the world do you do that without just wrecking the whole molecule? Well, that's the exact puzzle we're going to solve today. Okay, but before we dive into the nitty-gritty of how this all works, we've got to talk about the why. I mean, why is this one reaction such a big deal? What makes it so special? Oh, the scope it's just massive. I mean, if you're a student, you've probably seen this pop up on huge exams like the JEE or NEET. It's a favorite. But this isn't just about passing tests. Outside the classroom, this thing is an absolute industrial workhorse. We're talking about a reaction that's essential for making everything from super vibrant dyes to life-saving pharmaceuticals. It's basically the key that unlocks the door to a whole world of chemistry, the world of diazonium salts. So, here's our game plan for today. We'll kick things off with the chemical problem it solves. Then, we're going to peek under the hood and see how the mechanism actually works. After that, we'll check out the cool stuff it can make, see how it stacks up against its relatives, and wrap it all up with a final exam cheat sheet to make sure you've got this down cold. All right, let's set the scene. You know, every truly great reaction is a hero in its own story, right? It shows up to solve a really tough problem. And believe me, the Sandmeyer reaction solves a very tricky one. So here's the deal. You've got a benzene ring, and attached to it is an amine group, that NH2. This molecule is called aniline. Now, your mission, should you choose to accept it, is to cleanly chop off that amine group and stick something else on there, like a chlorine or a bromine. Now, that might sound simple, but it is way, way harder than it looks. Why? Because those aromatic rings, they are famously stable and just don't like to react. And enter the Sandmeyer reaction. This is our solution. It is such an elegant process. It uses this really special go-between molecule, an aromatic diazonium salt, along with a copper catalyst. And the result? You get exactly what you wanted, your substituted benzene, and the only thing left over is a little puff of nitrogen gas. So clean, so efficient, it's just brilliant. Okay, so how does this magic trick actually work? What's the secret? Let's pull back the curtain and take a look at the mechanism. Because this, right here, is where the real genius is. The secret is that it's not just one step. It's this really clever two-part process. The whole thing, the entire reaction, depends on creating this one crucial, super unstable molecule. Think of it as the perfect stepping stone. But, and this is a big but, to work with this thing, there is one golden rule. One rule you absolutely positively cannot break. And here it is, 0 to 5 degrees Celsius. This is it. This is the one non-negotiable, unbreakable rule of the Sandmeyer reaction. You have to keep the whole thing in an ice bath. If it gets any warmer, even a little bit, that key intermediate molecule we just talked about, it literally just falls apart. So please, burn this temperature into your brain. It's everything. Okay, so step 1, creating our star player. Here's what we do. We start with our aniline, we add some sodium nitrate and hydrochloric acid, and, you guessed it, we keep it ice cold. What we get is our benzene diazonium salt. Now, this molecule is the absolute key to everything, but it's so fragile, so unstable, it can only exist right there in that cold solution. You can't just make it and stick it on a shelf for later. It's use it or lose it. And now, for the grand finale, we add our copper ion salt. Watch this. The copper atom gives one single electron over to our diazonium salt. And that one electron, it triggers the most important moment in the whole reaction. The two nitrogen atoms, they see their chance, and they make a break for it. They escape as super stable nitrogen gas. It's this dramatic exit that literally drives the whole reaction forward. And what's left behind? A super reactive species that instantly grabs the halogen and boom, we have our final product. So that brings us to the big takeaway here. The fancy name for this whole process is a single electron transfer, or you'll see it written as SET. That single electron from the copper creates what's called an aryl radical. Think of it as a really angry, really reactive version of our benzene ring that just needs to bond with something now. If you're going to remember one word about the mechanism, make it radical. Okay, so we've seen how it works. Now let's talk about the what. What can we actually make with this amazing tool? And where do these things show up in the real world? Well, the Sandmeyer is famous for making 3 main products, and it does it incredibly reliably. All you have to do is pick the right copper salt. Use copper chloride, you get chlorobenzene. Use copper bromide, you get bromobenzene. And if you use copper cyanide, you get benzonitrile. Simple as that. And listen, these aren't just some random chemicals you'd only see in a lab. No way. These are fundamental building blocks for huge industries. That benzonitrile, for instance, it's a critical starting point for making a ton of azo dyes. You know, the things that give your clothes those bright, vibrant colors. And in the world of medicine, those other 2 products are often the very first step in a long process to build incredibly complex, life-saving drugs. All right, so the Sandmeyer reaction doesn't live on an island all by itself. It's got a few close relatives in the chemistry family, you could say. These are other famous reactions that actually start with the exact same diazonium salt, but they use slightly different ingredients to get different results. And trust me, it's super easy to get them confused, so let's clear things up right now. Okay, check this out. It's all about the key ingredient. For Sandmeyer, we know it's those copper-1 salts, CuCl, CuBr, CuCN, to get chlorine, bromine, or cyanide. Now look at the Gattermann. It's similar, but it uses plain old copper powder. And big difference, it doesn't work for the cyanide group. And what if you want to add fluorine? Well, you can't use either of those. You need a totally different reaction, called the Balz Schiemann. So the bottom line is the reagent you pick completely changes the outcome. All right, we have covered a ton of ground. So to wrap this all up, let's boil everything down to the absolute must-know facts. This is your final exam cheat sheet, the stuff you need right before you walk into that test. Okay, you ready? Here are the 5 things you absolutely have to remember. Number 1, the cold condition. Always, always write 0 to 5 degrees Celsius. Number 2, know your products. It makes Cl, Br, and Cn. It does not make fluorine or iodine. That's a classic trick question. Number 3, the mechanism keywords. Just think, diazonium becomes a radical, becomes the product. Number 4, what drives it? The escape of that superstable N2 gas. And finally, number 5, the path. If you see a question that says, go from aniline to something like chlorobenzene, you now know the Sandmeyer reaction is your answer. So there you have it. We've completely unpacked the Sandmeyer reaction. The mechanism, the products, why it's so important. Look, this is more than just another reaction to memorize for a test. It's a precision tool. It's a way to build molecules with real purpose. So I'll leave you with a final thought. Now that you have this powerful tool in your chemical toolbox, what would you create with it?